if it hasn't been good, I don't know. We're always glad to try to improve on it.
Thank you. Today I have last chance to speak at this conference. So I cannot avoid the main topic probably which we discuss and which is of main interest for me. This topic is toric mirror symmetry. So I plan to touch other topics, but I think this topic is very important, and I must speak about this. So the situation with toric mirror symmetry is the following. So there is a general idea about what mirror symmetry is, or what it should be, and there is a special version where, in this version we can understand much better because it has some nice combinatorial background. So if I and the problem is if I restrict myself to this combinatorial background and don't speak about general mirror symmetry, then it won't be clear why this combinatorial duality has something to do with a general idea of mirror symmetry. On the other hand, to speak about mirror symmetry in general, it's also very dangerous because many things are not clear and cannot be defined. So, but still, I would like to make a sentence about general mirror symmetry. So, mirror symmetry appeared in the following situation. So, one have X one Calabi-Yau and another Y another Calabi-Yau variety, and from each of these variety one construct a field theory n equals 2 super conformal field theory, and it turns out that sometimes two different varieties X so X totally different from Y, but the theory that they generate are isomorphic in some natural natural way using automorphism of this theory, natural automorphism of this theory. So what I said, of course, has no big meaning because I haven't explained how we construct a theory from Calabi-Yau and what is automorphism, what we want to and how it can happen actually that two really very different Calabi-Yau give isomorphic theory. It's really don't have good picture. And for this reason, I would like to make an example, which actually a very dangerous example, but still it's elementary geometry, which shows that somehow such a situation, it's not an example of mirror symmetry, it's analog of this kind of situation that I described just at the beginning. So elementary example of something that two geometrical objects, so one geometrical object x1, y1, two geometrical objects give isomorphic something isomorphic, but they are not isomorphic. And let me explain what I mean. So I would like to consider a cone, a lattice cone on a plane. So that lattice cone, that means generated by lattice elements. So just take a plane and a cone generated by some primitive lattice element, E1. So this will be my starting object. From this object, I will do the following. I will construct a, so these are two primitive vectors. I will construct a parallelogram just over these two vectors. So I have a parallelogram, so this vector. And then I will do with these parallelograms half twisting. Half twisting means that I shift the zero or origin to the center of this parallelogram. Why I say this half twisting? Because the point, the middle point, need not be a lattice point. It may be it's a half integer point. So it has. So now, so we go to we obtain some parallelogram, and we consider this object up to transformation of J and Z. That means transformation of lattice. So the first, the origin was cone generated by two primitive vectors. The result is parallelogram with twisted, shifted parallelogram. And we say that two cones are mirror symmetric if this construction gives isomorphic parallelograms. Well, of course, an interesting situation would be if we take just two cones which are which are equivalent up to. So we can take two cones which can be transformed to each other by phi from this. It is not interesting because then we get we'll start with isomorphic cones. Of course, they will give isomorphic parallelograms. But what would be interesting is to have non-isomorphic cones that give the same isomorphic parallelograms. And it's possible to do if we consider construction of this parallelogram somehow in two ways. I write this geometrically to have a parallelogram. We can consider this parallelogram as gluing of two triangles, like this triangle and opposite triangle. But we can take the same parallelogram and consider another two triangle, this and another triangle. So you can, if you, and it may happen that if you take these two lattice vectors, you cannot identify the cone generated by these two vectors with this. A simplest example would be just if we take some standard cone like 1 generated by 1, 0 and 1, n. So in this situation, when you have such a lattice cone, so generated by these vectors, we see that all lattice points in this parallelogram, they're just lying on this diagonal. But if we and if we shift, we get we get this. But if we look at construction of this parallelogram from another point of view, as if we took this vertex as an original origin, then the cone we'll get actually will be completely different. So, for example, if we take lattice points in this triangle, it will be not all lattice points in this parallelogram, it will be only half of these points. So we somehow the cone, one can prove that the cone we will get actually will be dual to this cone. So cone duality, I mean, so if you have a cone, maybe I should again, so if you have a cone sigma in the space in R, you can construct a dual cone in R just by the condition that the scalar product of xy is greater than 0 for, so it, sigma hat, it's all y's such that this scalar product is non-negative for all x in the previous cone. So, and you will see if you construct a dual cone, the dual cone will be isomorphic to the following one. So you take just this orthogonal to this side, and orthogonal to this side. It will be one point will be 0, 1, and another point will be n minus 1. So in this situation, you get some special cone, and you immediately see just from the structure of lattice point here and here that they are not isomorphic unless n equal not 1 and not 2. So if it's not 1 and 2, that we see that the cones are not isomorphic, but they generate the same kind of geometric object. And this example, I would like just to it's an analog of what happens in mirror symmetry. We start from two different geometrical objects, two different Calabi-Yau. They are not isomorphic, but after applying some functor, physical functor, they become naturally, become identified using some isomorphism. So isomorphism, I mean that I show here. So it was only example. Now I would like to go more. It's not well. You can think about what it's related to. But now I would like to go to toric geometry. So toric geometry and toric mirror symmetry is also based on the duality between cones. This is the best way of expressing toric mirror symmetry. So behind this toric mirror symmetry, again we have some duality between cones. But if we look, as I mentioned, we are mostly interested in some cones that appear as cone over polytope. So, for example, we usually we start with a polytope and construct a cone such that the polytope will be just one level of a section of a cone. So let me again repeat this situation. So we somehow have a polytope, then we construct a cone over this polytope, such as this section. And the question is whether we can, and this section is just defined by scalar product with some vector equals, U is vector in the dual space. So this is a picture in the space M, and this is and some vector defines the section, which is exactly polytope. Now we can ask, what happens if we go to the dual cone? And as we have seen already just in the previous example, we will get a cone, so dual cone, if it's cone sigma, then dual cone, which will be in the dual space, need not have such a property that all lattice points, that it will be a cone of a polytope. So only for some special cones, the dual cone will be of this nature. Actually, but we want to have such a property. So we want to have a property that also the dual cone is constructed from just as a cone over some polytopes. Here we have polytope delta, here we have some delta prime. And what does it mean? It means that by analogy, so there is a vector v on the original lattice such that everything, all lattice points, so generators of this cone, can be primitive generators of arrays of this cone. They line hyperplane scalar product equals 1. But v, actually, if this is satisfied, then the point v should be already lattice point in the polytope, because all lattice points in the polytope, they satisfy this condition. So that means if we demand that the dual cone has the same structure as similar structure as the original one, that means it's a cone over a lattice polytope, then we come to immediately that there is some special point inside V which is responsible for this condition. So actually, and vice versa. So the point, the vector u that define hyperplane should give you here a lattice point inside. So we come to a situation that, and actually, from this condition equals 1, one can easily see that it could be only one lattice point in the interior of polytope with such a condition. So now we have a duality between some restriction on polyhedra that generate duality between cones in this way, and this immediately implies the notion of reflexive polytope. So reflexive polytope you can write down definition reflexive polytope in the plane which is a affine section, or hyperplane which is a affine section. Then it will be then you can take this point V as an origin, or you can go to one dimension more and formulate reflexivity of polytope just in terms of cone. And in terms of cones, sometimes it's even more convenient, because when you are interested to application not for hypersurfaces and Calabi-Yau hypersurface toric variety, but also for complete intersection, this formulation duality between cones is much more elegant and for the mirrors, for the formulation of mirror symmetry. But it's equivalent. So reflexive polytope, it's a polytope such that if we take a cone over this polytope and go to dual cone, then the dual cone will be also cone over polytope, and moreover the point U and moreover this what I want to say, yes, and the scalar product of particular vectors of U and V and U is 1. So we have this if we some generalization of this notion appear if we take also some points, not necessary in polytope, but we assume that the scalar product is some other positive number greater than 1. But I don't want to speak about this generalization because it's not essential point. The essential point already one can see for this duality. So this is.
You're given a cone delta prime. How do you construct that base particle?
The polytope. Delta prime. How I deconstruct delta prime.
You start with your cone. You take a dual cone.
We start with a cone, and then we go to the to dual cone, and then we take all lattice primitive lattice points on arrays on one-dimensional sides. So we demand that all these points lie in one affine hyperplane. So and this affine hyperplane has distance 1 bit from origin. So that we will construct it in the same way as we have in the beginning. And this condition implies a very strong restriction on the polytope. So maybe I should also say that this, one can prove that for fixed dimension D, there are only finitely many reflexive polytopes up to unimodular transformation. So for dimension equals 1, you can see there is this reflexive polytope. In dimension 2, you have there is 16 reflexive polytopes. In there is a computer classification of reflexive polytope up to dimension 4. So in dimension 4 there are many millions. So this is somehow situation with this duality, but behind this duality, actually, this behind the toric mirror symmetry is exactly this kind of duality. You can formulate it in different ways. This transition from one space to dual space you can write down in terms of matrices, and you go to transpose matrices. If you write in coordinate relation, you go to the formulation that David Morrison explained in his lecture. But this is geometric way of looking at duality. Now I would like to explain further observations that also behind toric mirror symmetry. It's not only this duality between cones. It's also something related to cohomology of hypersurface in torus and some other cohomology. So let me explain what we had already at the beginning. At the beginning, we started with investigation of family of Laurent polynomials, m summation over lattice points, x to the power m, So this family of polynomials defines family of hypersurfaces in a torus. I will now consider the case complex number field or complex field. So it's a d-dimensional torus. We have family of hypersurfaces, and we also investigated cohomology of these hypersurfaces. So, as I remind you that cohomology, the interesting part of cohomology is so-called primitive part of in dimension d-1, so this hypersurface, and in degree d-1, and dimension of this primitive cohomology. Oh, I keep my notation, but so it's a normalized volume -1, or in other notation, degree of the polytope -1. So this is a primitive part of this cohomology. Moreover, there is a natural filtration in complex cohomology of this group. So there is a filtration, Hodge filtration, which is easy to understand. This Hodge filtration, the graded pieces of this Hodge filtration have dimensions, and the dimension can be computed explicitly as through coefficient of some polynomial. I will repeat again. So one considers the ring as delta. This is a ring and consider the generating power series for the dimensional homogeneous component of this ring. So this summation over k greater than 0, a number of lattice points in k delta, t to the power k. So this power series can be written as a rational function in the form 1 minus t to the power d plus 1. And here in the numerator one gets polynomial with non-negative coefficients, so it will be coefficients of psi 0 of delta, constant to actually will be 1, psi 1 t, up to maximal psi d of delta, t to the power d. So, psi, and this psi, they measure psi, I actually dimensions of homogeneous component of degree I of this of Jacobian ring. Jacobian ring as f is just quotient of the ring as delta by regular sequence f1, which is associated with the choice of this of our polynomial f. So this is what we have. Now, what I wanted also to remind you, we have also some kind of duality that I mentioned. This is have the reciprocity law behind this duality. So we can do the same procedure going to another power series if we count number of lattice points inside the polytope, okay, in the interior of the polytope, and the Q will be another polynomial of degree d plus 1 divided by d plus 1. So it will be another, we get another function, and this polynomial counts dimension of the module of the Jacobian ring. It's just this was ideal generated by interior points. Again, modulo this regular sequence. So, and we have this pairing between Artin module and Artin ring. This so this multiplication, and it gives a pairing between component I, d plus 1 minus I into d plus 1, which is isomorphic to C. So this is a situation that we discussed already for affine hypersurfaces. Now I would like to speak that there is another way of constructing cohomology starting with from the same data. So the data for us was simply polytope, but I would already mention that from any polytope you can go to one dimension more and construct a regular case. So you can put a polytope in this space you can go to another space. So now I would like to consider the case of polytope of this regular case in one dimension more, or maybe I will keep notation that the lattice will be d-dimensional. So now I would like to consider the following situation. I have a lattice of dimension d plus 1, m lattice. Oh, maybe it would be better to keep a lattice of rank d plus 1, and I have a polytope intersection of some cone. So, and now I would like to start. So the transition from this is standard. Now I would like to associate with this actually the same combinatorial data as I had before, only shifted in one dimension more. I would like to associate some of variety, and variety actually was already explained in the talk of David Morrison. Variety looks like as follows. So the main point in the construction is actually some short exact sequence. We assume that the finite set of lattice points has the cardinality n, and so we have these vectors 1 vi, I grow from 1 to n in our lattice, and we have a natural map from z to the power n to the lattice, which sends standard vector generators of this group in the corresponding vectors. So we assume that this map is surjective, at least after tensoring by Q. So that means if we go to real, for example, extension, we get a surjective mapping. And actually, we also had already some group which appeared also in the topic about hypergeometric function. This is a lattice of relations between vectors. So the lattice of relations, and of course it will be we'll consider just a real extension of this lattice. It will be on vector space. Now, if we have such starting from this short exact sequence, one constructs another variety, but this variety actually needs some choice. I want to explain. I want to remind you that actually, when we discussed the topic secondary polytope, we established that secondary polytope is actually so it's a Newton polytope of this principal determinant, and principal determinant satisfy d plus 1 homogeneity condition. D plus 1 homogeneity condition comes define actually a point in this space. So the secondary polytope can be considered as a line in the pre-image of some point under this mapping. So that it's on a affine happy plane which is parallel to kernel of this map. So the dimension of this space is n minus d minus 1, d plus 1. So, and here we have a secondary polytope. But now I would like to dualize this sequence. So I go to dual sequence. Here I will get a dual lattice tensored by R, and here I will get dual space. And in the dual space, we have another structure. Maybe I should explain just the idea. If you have a polytope in one space, then in the dual space you have a fan structure in natural way, because you can define a cone in the following way. So you take a point, and a point in the dual space, it's linear function on the original one. And you say that two points, they are equivalent if they attain minimum at the same vertex of the polytope. So you can make part for any point for any linear function, we can choose a vertex of polytope where will be when the minimum will be attained, and we say that they are in the same cone if it can be achieved in the same vertex. So then we get partition into cones, and it will be and this will be partitioned in exactly in this space where we have what was obtained after dualizing of this exact sequence. So now, what I want to do with this exact sequence, I take a point in this dual space, and as first, this is the first choice. But on the other hand, I would like to consider some function which is called Hamiltonian natural. It's a function from c to the power n to r n. This is a function just sorry, no, not just. I want to like to consider first a smooth map from Cn to Rn, which sends a tuple of complex numbers to just to square of module of them. So this is a map. But then we have a map alpha to our dual space. So we have R and star. So, and now we can do the following. We define the composition of these two maps, mu, and call this momentum map. So we moment map. So we take a moment map, we obtain some map, which is a smooth map, and if we choose here a point, we can consider the pre-image of this map. So pre-image, it turns out that the pre-image of this map topologically depends on the choice of the point. But actually this topology will be somehow locally constant, and topology will be the same if we take a point in the same chamber of this secondary fan decomposition. This fan structure that we get, it's called secondary fan. Topology will be the same. Well, and so but by this reason, we choose point always in some interior cone of maximum dimension of this fan, and we get a variety. And after that, we factorize this variety by torus. And this torus actually nothing but defined by as quotient of the real vector space modulo the lattice. So we just and this torus canonically embedded in the what was called also Dave lecture in the compact torus. So this is this construction is known in geometry or symplectic geometry as a symplectic reduction. If we consider Hamiltonian just a sum of squares. So with respect to this, so we have a torus action, and which respects this Hamiltonian, and this construction is just Hamiltonian. It's just a symplectic reduction. So by this construction, we get always this quotient is a symplectic orbifold, some variety. Of course, as I said, this variety depends on the it depends on the chamber where we have chosen this point. And moreover, topologically, as I said, for different points we'll get the same. But actually, from this construction, one not only obtains topological space, but one also obtains from this explicit Hamiltonian also explicit symplectic form. Symplectic form together with complex structure gives you also a Keller form. So in fact, what we get in this situation actually will be an algebraic variety, which is not, unfortunately, not compact. It's quasi-projective. So this variety, what we will get, this after making symplectic reduction, I would know it by xp, by torus. So it's smooth. Well, it's a quasi-smooth algebraic variety, algebraic quasi-projective also. Quasi-projective algebraic variety. Yes?
What was the torus and the previous?
The torus, what I have here. Maybe just again, let me remind you that we have this exact sequence here, and here, at least. Okay, this is not. So we have this lattice embedded in this. So we can just generate. We can consider this lattice just a lattice of characters of u1 to the power m. And this is somehow not characters, but one-parameter subgroups. No, sorry, it's we consider this lattice one, and the lattice sublattice define subtorus in a natural way. So you can write down this subtorus will be isomorphic to a real extension of this lattice modulo lattice itself. So, and it naturally acts. So I would like. It's the same construction as Dave Morrison, but I would like to prefer to keep splitting only for middle term of this short exact sequence and leave this non-splitting notation for other. But of course, it will be isomorphic to in this u1 to the power n minus d minus 1.
Maybe just one other question.
Yes.
You said that the topology of this symplectic reduction is constant along these chambers of
Yes.
Of this fan.
Yes.
Now, the fan depends on the secondary polytope.
The fan is determined by secondary polytope. Yes.
And your map, I guess, the second map, which depends on the secondary polytope.
No. Secondary polytope. No. Here I use only this short exact sequence. I don't need. Actually, I dualize the short exact sequence.
So it depends on A.
Of course, I said that it's the same data what it was at the beginning.
Right, but the first map you wrote down, the thing that takes Zi to absolute value of Zi squared, you just wrote that down. That has nothing to do with
No, well, we need to realize this. Of course, we can consider action of this group also on this variety. But so we realized actually this variety is subset here as so. It's very similar, but maybe, as you obtain, for example, projective space by taking a sphere of dimension 2n minus 1 and factorizing by circle action.
Right, I got that point, but your map from Cn to Rn
Yes.
corresponding to a specific Hamiltonian, I guess, right?
Yeah, yes, it was just exactly we take the I to squares. Yes, exactly.
But this statement about local constancy of the topology, does this work for other Hamiltonians as well?
No, I don't know. I want to consider just very special. Well, with the splitting, it's important that this splitting is important for me. So now, why I explain this. Why this variety is interesting for me from point of view of mirror symmetry. It turns out that I can say something about cohomology of this variety, but as I said, this variety is topology of this variety is locally constant. But now I would like, in order to get good picture, I would like to assume. So assume the point P lives in some fan of secondary in some cone, interior cone of secondary polytope, and this and cone of maximal dimension actually uniquely determine a vertex. So a vertex of secondary polytope. So that means it corresponds to some vertex of secondary polytope. But we know that vertex of secondary polytope is one-to-one correspond to convex triangulation of delta, this convex how of A. So now I can speak about P, I can attach to P some special choice of convex triangulation. And I assume that P is chosen in such a way that the convex triangulation is unimodular. Unimodular, that means that all simplices of maximal dimension, they have normalized volume 1. So they generate, so unimodular, all simplices, we can, as it is known, we can always get unimodular transform triangulation up to dimension 2. But in high dimension, it's unfortunately not the case. But sometimes you can do it. So for some polytopes. Now I want to put this special condition that it's unimodular. Yes. The point P, as I said, was used. It was a point. P was a point in the. And in this space, dual space, we have a secondary fan, and if secondary fan is due to polytopes, and if we take a cone of maximal dimension, then it gives you a vertex uniquely. Yeah, and then yes, exactly, and then we get convex triangulation. So convex triangulation, and we assume that this triangulation is unimodular. So if it's satisfied, actually, if in this case our variety xp is smooth, one can prove that we have also a covering by chart actually isomorphic to affine spaces. It's a smooth variety. It's still, well, it will always be not compact, but it will be smooth, and we can compute cohomology of this toric variety in the usual way. And it turns out that cohomology of this variety looks like as follows. So we take cohomology of this with integral coefficients. So actually we will be interested in the rank of this cohomology. So it will be 0 if I is the odd number, and it will be it will have dimension psi I of delta if I if I is 2k. So that means the same numbers that we obtained by as a dimension of pieces of Hodge filtration for a fine hypersurface, we obtain actually as cohomology, as even cohomology group of another geometrical object. So that means we can starting with the same data. Well, I would like to repeat again. Start with the same data, that means set of vertices, set of A. First, we considered polynomials and deformation, and look at middle cohomology, actually even primitive part of middle cohomology. But at the same time, we took another procedure, actually not more from a symplectic point of view, more natural, and we get a variety which has only even non-zero cohomology. Actually, one can prove that this cohomology all represented by classes of algebraic cycles, so it's the same as the kind of cohomology as you get for some homogeneous space or projective spaces. So, but the space, I would like to repeat again, it's not compact. So now this is the situation, and of course one naturally asks a question. Well, K here. It's just an index. I can take any letter. So K. I compute even dimension cohomology in even degree. And I get a sequence, and this sequence is exactly the same as I get for as coefficient of the. Yeah, that's only the idea. But we should multiply it by 2, so there is a because all cohomology are 0. So we get so in this somehow we go into another direction. We change.
So you're saying already cohomology must generate by recycle for this one?
Yeah. Yes. All this on. Sorry, I will repeat again. So all cohomology classes are generated by Chern classes of algebraic cycles. And actually, you can also compute not. It's even more natural to consider not cohomology, but I explain why. But some but k functor of this variety. So covariant sheaf, Grothendieck group of covariant sheaf, and because I will explain in a minute why it's more natural. Because if you compare the situation with affine hypersurface, so now we come to the situation. We have two objects, primitive cohomology of hypersurface. And it can be somehow identified with positive part of the Jacobian ring. And on the other hand, we have cohomology of this symplectic variety. And it turns out that the graded pieces here have the same dimension as graded Hodge pieces here coincide with graded weight pieces in another. So, of course, it suggests that there should be somehow probably a relation. But the first problem is actually we have this cohomology somehow doesn't depend on the change of the variety we get. We cannot deform complex structure, so there is no any dependence on complex structure. There is no deformation. But here we can deform the structure by choosing different polynomials. The deforming coefficient of polynomial, we get deformation of the multiplication in this ring. So that means if one wants to identify, to find kind of connection between these two objects, one should also be able to define deformation of multiplication on this object. And this is the idea of quantum cohomology. When we deform usual structure in cohomology with respect to some parameter. Of course, we can also ask about what will be a parameter. Parameter will be exactly what we don't what we have from our construction. We have symplectic form, and this symplectic form gives you also Keller form. So we somehow can speak about symplectic deformation of symplectic structure or deformation of Keller structure. So sometimes there are two possible languages. Either I think it's more common in physical literature to speak about Keller deformation. But from the construction, well, it's better maybe to speak about symplectic deformation of symplectic structure. So that means the cohomology will be as a Z model will be the same. But if you take a curve in a variety, then symplectic volume of this curve will change. So if you take a class, cohomology class, and curve with a given cohomology, the symplectic volume of this curve will be changed. And actually, this is what how one approaches this quantum cohomology. One should consider a map of curves. Actually, first rational curves, then of degrees of genus 0 with max points. And if one wants to consider high genus, then also there are some high genus Gromov-Witten invariant. But I don't want to go in details. I would like just maybe to show you one example of possible connection between these two objects in the case of curves. So one needs a really good illustration of this. Yes. Yes. Actually, this is exact. So the formation of symplectic structure you write down usually as power series expansion. And as we have already learned, power series expansion of anything from this left side, you will get if you go to vertex of secondary polytope. So solution of a hypergeometric system in explicit way, in a power series way, you can write down as if you choose triangulation. Actually, that means that the choice that we made here, the choice of triangulation, actually very natural for the first picture, because then you choose a point of secondary polytope, so you have discriminant, or let's say a determinant, and with respect to some vertex, you can so you get the secondary polytope, and you get a cone, and you take expansion through monomials in this cone. If you do go, so the secondary polytope lives in this space R, and the dual space can be identified with the Keller classes of this. So symplectic class. So we took P in the dual space, and we took P in some cone in the dual space. And this cone, where we took P, is actually due to, so if we take this cone as due to this vertex, then it will be due to each other, two cones to each other. So, of course, in order to identify the two deformations, we should go to some limit point. This is very important. Now, I would like to give an example how you do this limit point. Because there is an example where probably you can see something better. So again, example will be the case d equals 2. So d equals 2, that means we have a lattice polytope on a plane, and we assume that we have unimodular triangulation. In this case, we can always find convex unimodular triangulation. And then I would like to consider what does it mean for our hypersurface in torus. Actually, it will be a curve, a fine curve. So the triangulation, convex triangulation of this polytope defines some kind of degeneration of this curve. So let me explain this. My notes I mentioned something about topology of hypersurface over real numbers and complex numbers, but here it will be important topology over complex numbers. So one can do the following. We know that it's a curve, so it's just a Riemann surface with handles minus finitely many points. Finitely many points come from boundary because we don't compactify it. So now I would like to explain you how you construct actually this model. The construction goes actually from as follows. You take a primitive triangle and associate with any triangle a sphere minus 3 points. So you take a sphere and delete 3 points. Actually, it's topologically isomorphic to such an object, which is. And now the triangulation that we have, if we identify each this point with special with sides, so we make an identification these punctures with sides of the polytope. So if we have two triangles which have this, the same side, then we can just glue together this. And we can do this operation just from completely for all these triangles. So if we choose so many copies of punctured sphere and glue it together just from combinatorics of this triangulation, we get a topological model of this surface. Just probably as an example. Take a reflexive triangle, this simplest triangulation, then we get the following object. So we have just this triangle corresponds to this object. So here we have one more, and here we have also one more. So what we will get if we glue together, these points remain free. They correspond to outside points. Not compactification. So we'll get torus minus 3 points. And in this way, you can easily see that the number of interior points that you get in the polytope is exactly the genius of compactified surface. So I already said that S star of delta is genius of the geometric genius of this curve. So this is topology. But why I speak about such a, because actually this way of gluing together from Riemann surface from pieces gives you some filtration. Because the cycle, which along with make identification, they give some classes in one-dimensional cohomology. So that means, of course, we know that these cycles actually they live also on compactification because compactify. And on the other hand, we know that these cycles have pairwise disjunct. That means intersection number of this cycle of different cycles is 0. So there is the maximal dimension of space generated by these cycles could be only genius, because in H1 of compactified, so it has dimension 2G, but there is a symplectic form, and the maximal Lagrangian subspace has dimension. So that means this cycle generates some subspace of dimension equals number of interior lattice points. So that gives you filtration. As I said, we have a primitive cohomology of this affine curve. But in this primitive part, there is a subspace, natural subspace coming from, which has dimension. So there is a subspace, or say H. Dimension of this subspace is just number of points in the interior. Well, and I would like to somehow to say that this subspace already its approach to some graded structure that we need, because we need somehow this dimension appears as one coefficient of polynomial that we so the polynomial phi in our case I probably should write down. So the generating function for the ring S F plus will be as follows. So first dimension will be 1, but we deleted it, and then there will be a dimension number of lattice points in the polytope minus 3 and plus L star of delta t square. Yes. So this coefficient already appears. We can see this in terms of filtration. If we factorize by this piece, we get, of course, the complementary part, and this number is actually a number of Kelly deformation in another picture. So when we look at another picture, symplectic picture, we have a quotient. So we have our variety XP and cohomology. Cohomology. If we look at cohomology in degree, dimension of even dimensional cohomology, will be number of lattice points in the polytope, because it gives you a number of divisor minus relation between divisors. Because the cone will be live in three-dimensional space, you have three relation. So this is how. And if you go to next 4 XP, it will be exactly. So I would like to say cohomology actually is not a correct object to compare. The best object to compare will be a reduced K-series of covariant sheaves. So we take functor of XP, because it's algebraic variety, and take reduced. That means we consider this subgroup natural splitting of K into Z, which is defined by rank, and so it's like again an analog of primitive part. And this should be compared with primitive part of K. We have also some filtration on K group, and we don't need grade structure. We need only filtration. So we have filtration by dimension of support, and it can be compared with cohomology. Yes, with the filtration that we will get on cohomology or primitive cohomology of hypersurface. So this is an example, at least, where we can make pieces of this identification more visible. But of course, it's just because of this advantage that we have unimodular triangulation. In general, we don't have such a triangulation, and it leads to some to idea that we need another kind of cohomology theory, Oberford cohomology, in order to be able to identify two cohomology that we appear. One is cohomology of a fine hypersurface, and another is cohomology of quasi-projective rational variety that you get using this actually symplectic stuff. But I think I should stop.